Oh.
Okay, ladies and gentlemen, what happens when you mix an acid and a base together?
They neutralize.
And they form a
Salt and water.
salt and water. What happens if you take that salt out and then put it in water?
You got one.
Come on, what happens? You make
A reaction.
You make a neutral base.
okay, come on, you can do this. Acid plus base equals salt and water. Salt plus water equals acid and base. I'm certain you needed that little motion deal. That is exactly correct. Okay. So salts are formed from an acid and a base combining. Here's the salt, here's the water. So we have the anion and the cation reforming to make the salt. If you have a strong acid and a strong base, they are going to form a completely neutral salt. So HCl and NaOH will form NaCl, which is a neutral salt. It comes from a strong base and a strong acid. I don't think this takes a lot of brain power. If you take a weak acid and a strong base, the resultant salt is basic. If you take a strong acid and a weak base, it's an acidic salt. No problem. Today what we're going to talk about is hydrolysis. How many people remember the word lysis from bio? To break apart. What does hydro stand for? Water. So this is water breaking things apart. Water splitting. It's the reverse of a neutralization reaction. It must be written in net ionic form. You love net ionic form, right? No problem. You can do those. And you write it for all soluble salts. You memorized your solubility rules, right? Say yes. Yes. Say yes.
What?
All right. So, this is the bane of chemistry kids' existence. It drives them nuts. There's steam coming off a chemistry kid. They find it incredibly difficult and very, very irritating. You know what happens? I teach you how to do that. You kind of growl at me. I kind of growl back at you. And then we move on. Until last year, maybe the year before. I'm teaching this, I'm looking over, and and kids are barking back at me and everything else. And I look over, and this girl has drawn this little figure on her paper. And she is just like, da, 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 da. I said, what are you doing? And she explained it to me, and it was brilliant. So then I went with a bunch of AP teachers, and I showed them this thing, and they said, it is brilliant. So I took credit for it. So now on, it's my method. It's called, you know what, I cannot remember.
Oh, you stole her method.
I stole her method, and now I don't even remember who it was. I think it might have been the year before.
I hope she's watching this right now.
Maybe. Okay, I'm going to call it the 4-square method because that's what it looks like to me. So what you have to do first is determine the parents of a salt. What are you talking about? A salt is an inanimate object. It has no parents. Yes, it does. Look, here are salts. And let us recall that a salt is nothing more than a ionic compound. So, part of this came from the acid and part of it came from the base. The base was KOH. The acid was HNO2. Name that. Potassium hydroxide. Name that.
Nitric acid.
Nitrous acid. Strong or weak?
Strong.
Strong or weak? Weak. Weak. Okay. Let's just for grins Run over strong and weak acids one more time. As I no sober class clowns in Hawaii. No sober class clowns in Hawaii. 2, 4, oh, sober. Okay. All right, got it? Strong. What is a strong base? That's it, okay? That's it. All right, let's try this one. The base. The acid. Strong or weak?
Weak.
Is it group 1?
No.
Weak.
Strong.
Strong. Is this going to make an acid salt or a base salt?
Base.
Acid salt or a base salt? Okay. All right, so far, I think you can do this. I think you're a little wonky on this, but you'll be okay. These 3 things require that I show you the example, and then you'll get it. Here is the example. Write the hydrolysis reaction for NaCN. Okay, I cleave it in half into its ions, and I write Na plus, Cn minus. Then underneath, I write the parent. Na comes from NaOH, Cn minus comes from the HCN. Then I inspect them to see which is strong and which is weak. This is weak. It says to cross out the strong. What that means is you cross out the cation of a base or the anion of a strong acid. So I cross that out, cross that out. The top line is my reactant, the bottom line are my products. Every hydrolysis reaction must start with water. What's left over on my reactant line is CN, and then I write what's on my product line. Remember, when I cross out the cation, the OH has a charge. If you neglect to write the charge, it is wrong. Okay, so let's go back to this and do our little 4 square thing and write K plus NO2 minus comes from KOH and HNO2. These are the reactants, they come first. These are the products, they come second. I'm going to cross out the strong. To write my reaction, I start with water because you can't have hydrolysis without it, plus my top row. Will this be acidic or basic? Well, it's basic. There's free OHs hanging around. Do this one and this one for me. 4 and 5. 4 and 5. Hello. Thank you. Got more? Are you done? What are you supposed to do? Look at your directions. Okay, this one. Okay, my strong is NaOH, my weak is HClO2. So I'm going to cross this out. I start with water. The only thing left in my reactant side is this. And then on my products, on the bottom. Good? Okay. So I'm going to have reactants and products here. Here's Na, here's Cl minus. Comes from NaOH, comes from HCl. This is strong, this is strong. So this is gone, and this is gone, this is gone, and this is gone. Water has to be a reactant. Oh, I get it. This one is, all right. Okay. Moving on. All right. What if someone is really mean to you and says, determine whether this salt is acidic or basic? What do you do? Ask the teacher. Nope, I'm not helping. Okay, this comes from NH4 OH. That was kind of scary. This comes from, thank you, acetic acid. Both of them are weak. I know that the Kb for this is, I think, 5.56 times 10 to the negative 10. I do for sure know that the Ka for acetic acid is 1.8 times 10 to the negative 5th. According to this, it says if both are weak, compare the Ka to the Kb. Okay, Kb to Ka, which is larger? So this is acidic. All right. Nobody in the scope of this class is going to make you do anything other than that. Okay. Let's move on to the next progression of these problems. So far you have been doing qualitative work about finding if it's an acid or a base. It's time to be quantitative. So, here's how you do it. You write the net ionic equation for hydrolysis. You just did that, you're a pro. Write the equilibrium expression. You can do that. I've seen you. Find Ka or Kb using Kw equal Ka times Kb. Look, just to mess with you, actually it makes a lot of sense, we'll see this later. Ka is given if the solution is basic. So you're going to have to find the opposite. If you have an acidic solution, they're going to give you a Kb. Then using a rice table, find the concentration of the hydroxide ions or the hydrogen ions. All right, the further you get in chemistry, the shorter the problems become. They should kind of scare you when they're just a few words. This one says, calculate the pH of a 0.3 molar sodium fluoride solution The Ka value for HF is 7.2 times 10 to the negative 4th. Huh. Okay then. What's the first thing to do? Okay, we can do it. Here's a line. I'm going to make use of it.
Oh, wow.
All right. Here are the ions. Here are their parents. Top line's reactants, bottom line's products. Cross out the strong. Making sure to turn this into an ion. Starting out water plus the fluoride ion yields hydroxide ion plus hydrofluoric acid. Yes? Write the equilibrium expression. What do I want here? What is the equilibrium expression? This part we got. I left water out. Why?
Because they're liquid.
Pure liquid can't fool you. Now, what controls the pH out of all of these things?
The concentration
Of
of hydrogen,
the hydroxide ion concentration, because is this a weak or a strong acid? It's weak. So are there going to be a lot of hydrogen ions floating around? Nope. So this will control the pH. Therefore, I need Kb, not Ka. And to find Kb, I will take Kw, 1 times 10 to the negative 14, over Ka, which is 7.2 times 10 to the negative 4. Kb is going to be equal to, you know, I keep on losing all my math, so somebody's going to have to be my math person. 1.39? 1.39 times 10 to the negative 11. All right, now I am ready to start my rice table. This doesn't belong. Here's my initial concentration. The fluoride ion is 0.3 molar. How do I know that? These are soluble, and they completely ionize in water. So if I have 0.3 molar NaF, I have 0.3 molar Na ion, I have 0.3 molar F minus, F minus ion. None of this and none of this. We always know in acid and base work, these are the changes because things happen one at a time. So, substituting into my equilibrium expression, 1.39 times 10 to the negative 11 is equal to x squared over 0.3. Oh, still dropping that down here. X is equal to 2.09 times 10 to the negative 6, which is equal to the hydroxide ion concentration. The pOH is the negative log of that, which is 5.69, and the pH would be 14 minus 5.69, which is equal to 8.31. Good? All right, let's try another one. Calculate the pH of a 0.1 molar NH4Cl solution. The Kb value for NH3 is 1.8 times 10 to the negative 5th. All right. Here we go. Hydrolysis reaction coming our way. NH4 ion and Cl ion. NH4OH and HCl. These are the reactants. These are the products. Which one is strong? One's right here. Make sure I put my charge there. So water begins, plus what's left on the reactant ledge, and then underneath my products, NH4OH plus H plus. Okay. Where does this come in? This is something that you were supposed to remember. That NH4OH does not exist as a product. When you get it as a product, you should remember that it decomposes into this. Got it? Just like you were supposed to remember when you had H2CO3 as a product, it decomposes into this. This is your this is your Coke sitting out, and the carbonic acid always breaks apart into the bubbles, leaving your Coke and the water. So back to this. Now, let's write our everything that's going to play in our rice table then. This won't. This actually doesn't exist. This won't. So I'm left with this, this, and this. So this is on the reactant side. This is on the product side. And there we go. Now I see what the deal is here. Our equilibrium expression would be NH3 over H plus over NH4 plus. We're going to need a Ka because this is controlling the pH. Who has done the Ka for this?
5.56 times 10 to the negative.
Okay, thank you. All right, starting with our initial concentration, this is 0.10 molar. This is 0 and this is 0. Substituting in 5.56 times 10 to the negative 10th is equal to x squared over 0.1. X is equal to anybody? 7246? Times 10 to the negative 6. So our pH is going to be the negative log of that, which I'm hoping is going to give me 5.13. Good. All right. So really, those aren't so terrible, are they? Huh. All right, I don't want to do this one because it forms this funky coordinate complex, and I'm betting you're not going to see that again. It's out when they revise the test. I'm going to hope that they didn't bring it back. Same with this part. What I want to talk about now is how you are going to identify Lewis acids and Lewis bases. And the way you're going to do that is you're going to have to look at the, you're going to have to look at the, come on brain, work, Lewis dot diagrams. So if they asked you if these were acids or bases, the first thing you'd have to do is draw the Lewis dot diagram. And I'm certain you could do that. It might take you a moment to refresh yourself, but you could do it. You need to remember a Lewis acid accepts an electron pair, a Lewis base donates electron pair. So here they are drawn for you. I look at pH3 and see that the central atom has a pair of electrons just hanging there, so it must be a base. I look at boron, it is lacking an octet, so it's able to receive another set of electrons around it, so it must be an acid. I look at H2S, and it has a spare electron pair, so it can donate. And SF4, I think, I'm not really sure until I recall that sulfur is in the third period or higher, so it can expand its octet, so it actually could take another pair of electrons, therefore it must be an acid. Good? Alrighty. One more thing, and then we're done for the weekend. Well, actually, I am, you're not.
Oh, yeah.
Nah, I still have stuff to do too. All right, I want to use this formula for titrating strong acids and bases just for the time being. Strong acids and strong bases. All right, the molarity of the acid times the volume of the acid times the number of hydrogen ions of an acid at the equivalence point, which is usually when you get that color change, is equal to the molarity of the base times the volume of the base times the number of ions of the base. In essence, what you're doing is you're finding the moles of the acid. Then you're finding the moles of the base. Then you're comparing them to see which one is in greater concentration. Then you find the molarity of the excess by dividing it by the total amount of the solution. Here we go, watch. Calculate the pH of a solution containing 25 mils of 0.005 molar HCl, strong, so we can use this, and 45 mils of 0.003 molar KOH, also strong. So starting with the acid, 0.005 times 0.025 liters, remember we have to have it in liters, times 1 proton. That gives me 1.25 times 10 to the negative 4 moles of acid. On our base side, we have 0.003 molar times 0.045 liters times 1 OH gives us 1.35 times 10 to the negative 4 moles of OH. Which one's bigger? The OH is. By how much? Subtract and find out. Everybody agree with me so far? Okay. To find the molarity of that, I would take the moles of the excess over the total volume of the solution, which is 0.07 liters. That gives me a molarity of something that I can't remember. Times what? 4? Okay. That is equal to the hydroxide ion concentration. So the POH is equal to the negative log of that. And the pH is equal to 14 minus that, which is something. What was the POH? 3 point what? And there you go.